Hi, everyone. I am Esther de Nicolás Benito, Senior Director of the Strategic Missions and Technologies team here at Microsoft. Earlier this month, Microsoft and Continuum announced they had demonstrated the most reliable logical qubits on record, with an error rate 800 times better than physical qubits, unlocking the next level of reliable quantum computing. To share more about this achievement, I'm very excited to be joined by Dr. Jennifer Strapley, Senior Director of Offering and Product Management at Quantinuum, and Dr. Krista Zvore, Distinguished Engineer and Vice President of Advanced Quantum Development at Microsoft. Jennifer, Krista, welcome.
Thanks, Esther.
So Krista, Microsoft and Quantinuum have been collaborators for quite a while now. How was that collaboration over these past years? How has it evolved, and how did it get us to where we are right now?
So we started collaborating back in 2019, and that was really around Azure Quantum, right? We had a partnership to bring the Quantinuum hardware forward as some of the first quantum computers in Azure. And really the idea was to bring quantum computers to people around the world, to enable people to use and develop on quantum computers, try them for the first time. And so now over the years, though, we've become very focused on accelerating scientific discovery, right? Both of our companies are very interested in seeing quantum advantage, right? And being able to show that you can do something with quantum computers that you can't achieve with classical computers alone. And so in this work together, over the years, we've become more focused on how do we go about enabling that? Well, one is we need different representations and languages, right? We need different ways to express quantum algorithms and the software stack down, those representations down. So we worked very early on together around the quantum intermediate representation, which is an open source representation. And Quantinuum was one of the earliest, founding partners in the QIR Alliance. And so that's been wonderful to work on together. Additionally, we've worked on demonstrating different aspects of, different types of circuitry that are needed for quantum algorithms, repeat until success circuits, distillation circuits. And then in this work, really taking a big step forward towards fault tolerance, right? Really working to show that we can achieve reliable quantum computing together.
Yeah, the relationship has been fantastic. And one of the things that I've always valued about the Microsoft relationship is it's very purposeful. Everything starts with a goal in mind, and we work very focused to get to that goal. That's not always the case. Sometimes when you have collaborations, they're very cosmetic. And I'd say in this case, it's a great example of how focused and how productive a collaboration can be. We're both full stack quantum computing companies. That means we have hardware and the layers of the hardware above it and software and applications. But we're very like-minded in that we both see a very similar promise for quantum about how we go make this solve problems in the world. So it's been a really ideal partnership. The places where we have skills that are very complementary were key here in this partnership, but we also have areas of overlap. And in this particular case, we mobilized those areas of overlap to help solve this problem faster. This particular effort, we only really worked on for 2 months together. And it's pretty exciting what we got done in about 2 or 3 months' time.
And I think that's where really bringing the teams together, right? We have folks from, the top of the stack down to the bottom of the stack, right down to the hardware, really coming together to optimize across the whole stack to get this all to work.
It takes that because these are complicated machines. And the Microsoft team had to understand a lot about our hardware. We had to understand a lot about what was driving their error correction code. And as issues came up and solutions needed to be figured out, having that knowledge, having that close relationship allowed us to be very agile.
That is fantastic. And I can imagine the amount of teamwork that is required to achieve this in just 2 short months. That is incredible. Which takes me to the next question, which is about the recent news, the milestone. Microsoft and Continuum have delivered the most reliable logical qubit on record. That's a big statement. Tell us more about this big breakthrough.
Yeah, so, I think to understand the achievement, we should first take a step back and understand what is a logical qubit, right? What does it mean to have these logical qubits? And really, what we've understood over the years is to do something incredibly valuable with a quantum computer, right? And really with a quantum computer paired with high performance computing with AI, we need to make sure that that computer can give a reliable result, and that it can, produce that result over and over reliably, right? Give you the correct answer. But to do that, to achieve what we call practical quantum advantage, to have that kind of better or faster capability from a quantum machine, we've come to understand that you must have logical qubits. And really, I like to think about logical qubits, think of it like a virtual qubit, right? It's a qubit that's created from a pool of physical qubits. So you use these physical qubits and you operate on them as a unit. And it really is a careful orchestration across these physical qubits that's required, such that that logical qubit, or this virtual qubit, becomes better than any one of those physical qubits on its own. And that's the key, right? We want to get to the point where these virtual qubits, these logical qubits, are better than the physical qubits themselves, because that's the unlock for doing very deep, long quantum computations, right? Once we get to deep, long quantum computations, well, that's where that advantage sits, right? That's where we can see being able to solve scientific problems, commercial problems, better or faster than we can with digital computing alone. But these logical qubits have to satisfy a set of criteria in order to then be used in a computation to achieve this practical quantum advantage. So we need these qubits to first be better than their physical counterparts. And it needs to be quite a bit better than the physical counterpart, right? So we need a good separation. In other words, we need a lot of improvement in the error rate on the logical qubits compared to the physical qubits, to that physical error rate. So we want to see this really, big gain, this big improvement in error rate. We also want to be seeing that we're correcting the errors, right? We need to be able to take care of the errors that occur in the computation, correct them, and then continue computing, right, in order to achieve a reliable result. And the third criteria we need is we want to make sure that these logical qubits can be entangled, right? So that means you need two or more of them. And so when we take these three criteria, what we've achieved together between Microsoft and Quantinuum is that we have satisfied all three of these criteria. In particular, we now have logical qubits that are showing an 800 times improvement over the physical error rate. And that is the largest improvement to date. And we have not just one logical qubit here, right? We've enabled 4 logical qubits that are 800 times better than the physical error rate in terms of their logical error rate. And we've satisfied all three of these criteria. So this is really like taking something that used to be kind of like having one error in roughly 100 operations and getting it to the point where now you have roughly one error in 100,000 operations. So it's a big gain.
Yeah, so our role in this project was to provide the best possible hardware we could and let Microsoft use their error correcting codes on top of our hardware to see together what we could do with this logical qubit, or Microsoft's the first one to call it a virtual qubit, which I think is a really good way to see this. So with these error correcting codes, you have to do a lot of operations at the physical level. And to date, many of the times that people have done the error correcting codes, the answer has been worse because you do so many operations, and these operations on the physical level have noise associated with them. After you've done all of these operations, sometimes injecting the error correction leaves you in a worse place than you started. So it really requires very, very high fidelity physical qubits to start with. And that's what our platform does exceptionally well. So at Quantinuum, we've been working on really generating the best physical hardware that we can. This is commercial hardware. It's available on Microsoft Azure. It's our system model H2 quantum computer. And it's available and runs robustly, repeatably, and gives the same answer. And I think that was very critical for the Microsoft researchers to know if they ran the code at night, if they ran the code in the morning, if they ran the code on a weekend, didn't matter. You got the same answer from our quantum computer. And I think that itself is a story here as well. So our architecture is a unique architecture in that our qubits actually move. They're not stationary. This provides some advantages that I think the Microsoft team took advantage of. We call those the connectivity of it. We call it all-to-all connectivity, which I think was important. Also having very, very high fidelities, as I said, with our 2-qubit gate error being 99.8, almost 99.9% fidelity. And in this case, we learned a lot when we do all of these QEC codes. That's been our experience in the past. These QEC codes are really truth tellers for your hardware. And we learned new things about our hardware and what were some of the things we came up against. As we came up against those things, we worked really shoulder to shoulder with Microsoft to find solutions and help drive to that eye-popping result that's being presented.
I think what's exciting, right, as Jenny has been saying, right, you have to have something be repeatable, right? You have to be able to do it over and over and get the same result. And I think that's what has worked, amazingly well here. We have run these instances 14,000 times, actually more than 14,000 times even. And, we're getting the same results. In 14,000 runs, we've never experienced a failure. And that, I think, is a very, very compelling and thrilling result to see come from the hardware. When we scan across the hardware landscape, right, Quantinuum's hardware stands out. It has some of the best, or if not the best, quantum volume in the industry, right? As Jenny was saying, the 2-qubit fidelity is impressive. And when you go to run these error correction protocols on hardware, not any hardware is going to be able to do it, right? As Jenny outlined, right? Sometimes you run it on hardware and the error correction protocol will cause the whole thing to be worse. But this is what's very special about the pairing here. We've invented a series of error correction codes and protocols. We have heavily optimized that for the Quantinuum hardware. And the Continuum team has worked hand in hand with us to optimize these capabilities and then enable for the first time to show this extremely large improvement in error rate on logical qubits. And it's been thrilling to do this work together, right? To really overcome this huge hurdle that's existed in the industry. And I think what's even more amazing, for me personally, having worked in fault tolerance and error correction for, well beyond 2 decades now, it's really thrilling also to see that we can do something called syndrome extraction. This has been a very large milestone for the industry, to be able to show that without destroying the data qubits, without destroying these virtual qubits, we can extract and diagnose errors, so we can perform these error diagnostics, as well as understand how to correct those errors without, perturbing the logical qubits, right? We need those logical qubits to continue computing in order to do a really long computation. And those computations are needed to show scientific advantage, right? To get something better or faster than what we can get classically. And for the first time in the industry, and this is something I've been waiting to see for, 20 years, right? I wrote about this in my dissertation, to actually see it working, Continuum and Microsoft, to show this works. I just think it's an absolutely, it's a heartwarming moment for me to get here.
You've been hinting at some of the reasons why this time it is a very different milestone that has been achieved. And I love the practicality. There's a number of themes that are popping. The practicality of it, the fact that it's a collaboration, the fact that, it's the industry coming together and solving these big hurdles. I would like to spend a minute to bring it again home. Like, why is this time such a different announcement of this is a logical qubit. This is the moment that we get to the next level of reliable quantum computing.
Yeah, there's a lot of momentum in error correction, both work that Quantinuum's done, work that Microsoft's done, work that others in the field have done. And every one of these achievements has moved the bar forward and forward. I think when Microsoft came out with their criteria for a logical qubit, it was the right time to publish that because there was ambiguity. What is the right bar to set? I think Microsoft set the bar even higher with that blog and kind of putting a framework and putting a perspective in place about how the industry can think about logical qubits. And so we adopted that. We had very like-minded thinking about what that bar should be. And that was the exciting thing to work with Microsoft on. This new bar is set, and we're going to work together on it. Every time you set one of these bars, then all the industry races to get there. So I think this announcement will mean that there'll be a whole bunch of new people getting for these results. And it also opens the aperture on what you want to do with the results. I know both of us probably have more than a dozen things that we want to go do now together to take advantage of this new technique. What's really different here, as you said, is the collaboration, but also the eye-popping results. 800x is something that's significant. I'd say probably we got there as a team faster than the industry would have thought.
Absolutely. I think building on what Jenny has shared here, right? This 800x is a large improvement. I think we were all just ecstatic to see that number pop out, right? After running this many, many times on the hardware, seeing that number, it's just this huge piece of information that just really helps you be convicted that you're on the right path, right? You know, you're internalizing that, yes, we are able to reliably quantum compute, right? We are able to say we are now at level 2, the next, and heading through level 2 to get to level 3. We want to see scientific advantage from quantum machines, right? Solving problems that we can't solve classically. We want to show commercial advantage with quantum machines. And I think it's important to recognize that when we say solve that with a quantum computer, right, this is still hybrid, right? These solutions require having a classical machine in the mix. So it's really about getting to the point where we have a hybrid classical quantum supercomputer that enables scientific and, commercial advantage. I think with these results, what's really different is we have a very large improvement. We have multiple logical qubits. We've shown entangled logical qubits, and we've shown this multiple rounds of syndrome extraction, which means that we can maintain that error diagnostic system. We can continue to run error diagnostics and corrections while the logical qubits are able to compute and stay alive. That has never been done before, and that is what's needed to enable long computation with quantum computers that's reliable.
With this excitement, I'm feeling the excitement, and I would like to share it with the community. What does this mean? Like, what does this milestone mean for the whole field of quantum computing?
Yeah, so we've talked a lot about these levels, right? And so I really view it in this simple leveling, right? There are 3 levels of quantum computing, of implementation of quantum computing. Level 1, you have foundational, right? These are your physical qubits, NISQ machines, noisy intermediate scale quantum machines. Every machine starts as a NISQ machine, right? You operate it with the physical qubits. Not every machine can make it to level 2, where you show resilience, right? The ability to perform resilient or reliable quantum computing, where you're using logical qubits to create a better computation than you could physically. And this is where, in this level, we can start to see scientific advantage when we have upwards of, say, 100 logical qubits operating together and able to compute, right, longer computations. And then at level 3, you have scale. There you have a quantum supercomputer where you have upwards of, say, 1,000 logical qubits, and you're able to demonstrate commercial quantum advantage, right? So these simple levels, right, I think really break down where are the different quantum computers. And again, not every quantum computer can go from level 1 to level 2. It's really this special pairing, right, of error diagnostics, error correction capabilities, paired and optimized for quantum hardware, the right quantum hardware that together gets you into level 2. And that's what we've done here between Quantinuum and Microsoft. And I think the industry should be excited about this because, hey, we're here for quantum advantage, right? We want to see problems solved. We want to accelerate scientific discovery. We want to help save and feed our planet. We want to create solutions, right, that leverage this hybrid classical quantum supercomputer, right, that really quite literally help save our world, help society, help humanity, clean water, clean energy, right? All of these problems, we need more accurate solutions than we can have today, and it's going to come from pairing with quantum machines. And so I think the industry should be excited because we are now squarely in level 2. We are on path to level 3, on our way to showing true scientific advantage for problems that we care about with quantum machines.
So that brings me to the next question. What should the industry customer, the industry decision makers, take away from this announcement?
So in this result, right, we have entered level 2, right? We have entered the level of resilience. We have reliable quantum computing, working. There's still a lot more to do. But I think for the industry, it's important to recognize the achievement here, right? With this multiple rounds of syndrome extraction, with such a large improvement in the logical error rate, we are on path to being able to build, right, a hybrid classical quantum supercomputer, right? We're on path to being able to show scientific advantage with such a supercomputer. So I think that's a key takeaway. And not only that, right, even in advance of having, the 100 logical qubits or around 100 logical qubits needed to show such scientific quantum advantage, even in advance of that, one can prepare already today. So we have integrated Quantinuum into Azure Quantum Elements. We have run chemistry calculations on that quantum hardware. We are gearing up to enable that with the logical qubits and the capabilities we've talked about, in this discussion today. But already you can prepare your workflow, right? So these workflows, when we think about computational chemistry, different scientific discoveries you want to do, say in Azure Quantum Elements, it's really about understanding when and how to use the quantum machine. The quantum computer piece of that workflow is really good at high accuracy for certain problems. And this is where in the Azure Quantum Elements workflow, right, you can run AutoCast, you can understand where do I have these strongly correlated electron problems. And when you have that, you can then prepare and run on the quantum machine. And already today you can try that workflow, you can build that workflow, you can try this capability. And so I think that's really exciting for the industry, that there is a proof point on how to go do this. It exists in Elements today, and you can try it.
I like the word proof point for this. I think this is a critical industry proof point. Many in the field think you have to wait until you have those hundreds of thousands logical qubits before you can go do anything with them. And I think this proof point sets out to say, no, you don't have to wait. There's equipment, both at the hardware, the software, throughout the stack that's getting developed, and companies that are seeing that their next frontier is in using quantum to disrupt their own businesses are now be able to start thinking, okay, it's time to start mobilizing my team. It's time to start mobilizing my scientists and engineers to understand how do we put quantum into our business. There's tools that are out there today. Krista mentioned Azure Quantum Elements. We have a tool called Inquanto. It's really focused on the quantum part of that. Today, those tools are very complementary to help people think about how do we get started? How do we start our innovative journey on quantum together? We're excited to see what customers now do and bring their own use cases, whether it be in chemistry and materials or something else where people are looking for quantum advantage. We're excited to see that people use this new capability and excited to see what they do with it.
And I think that's so important, right? Because it's not going to be just our teams that come up with these solutions, right? And there's no shortage of learnings when you work on the real thing, right? When you work on that hardware, you work in the complete workflow, the full environment, you learn so much, you can create so much. And I think we both recognize it's not just, our teams of folks that are going to create these solutions. It's that collective genius around the world, right? It's people around the world thinking about different types of problems than maybe we are, who then come to this capability, start to use this capability, create new things with this capability. I think that's where the real discovery sits, and I'm so excited to see what people do with it.
One thing that I'm finding very inspiring in listening to both of you is that this is not about technology for technology's sake, right? There is a purpose and there is a sense of, solving real problems. And I think that's what meaningful innovation is innovation that can really solve some of the world's greatest challenges. And I love how focused on solving the problems you both of the companies are. So this is very inspiring. Before we wrap up, is there any final thoughts that you would like to share with the community?
We've worked together for many years, but this really hit the floor in about February, and here it is April, and it was only a 2-month effort. Think what we're going to do in 4 months and 6 months working together. So really excited about this first result, Really excited to see what customers do with it, and really excited to see what we'll do next.
And, at Microsoft, we think a lot about empowering people and organizations, enabling them to achieve more. And I think what's really exciting in the work we've done together here with Quantinuum and Microsoft is that we have really brought together collective genius, collective creativity, collective innovation. We've sat around the table together, and together we've been able to achieve more so that others can achieve more, right? I'm really excited about bringing this forward to the world. I think a lot about, leaving this capability, with our children, right, with the next generation, so that they can solve, the world's next set of problems, right? And I think this is we're on path to being able to do that, and that just thrills me.
Wow, this was incredibly inspiring. Thank you so much, Jenny and Krista, for being here today. And thank you, everyone online, for joining us. If you would like to learn more about how Microsoft and Continuum developed the most reliable logical qubits on record, please visit the resources on screen. For those of you joining us live, members of our engineering team are standing by to answer your questions. Thank you, and until next time.